My name is Mark Greenman. I'm a research fellow and teacher-in-residence in the physics department here. I work closely with Andrew Duffy and Bennett Goldberg, who are both here. And the project that Andrew was referring to is our AP, based on the AP Physics, edX AP Physics 1 original MOOC that has been significantly modified, though, to direct and to serve the needs of high underserved population students, at-risk students, such as many of the students at Boston Public Schools. So that's what the goal of the project is, to attack this national problem of closing the STEM learning gap for underserved populations. The project team is Andrew Duffy and Bennett Goldberg, as well as myself. So as in the first slide, you saw the discussion about reaching underserved populations, African Americans, Latinos. We're working with 7 high schools throughout Massachusetts, 4 of them in Boston Public Schools. Boston Public Schools exactly replicates the kind of target population we're looking at, with 75% identifying themselves as African American or Latino. Of the 34 high schools in Boston, only 4 of these high schools offer AP Physics. So students across the nation in underserved situations are denied the opportunity to take these kinds of courses, and hence immediately are behind the 8 ball in terms of being successful in coming to colleges and going into physical science type courses. Of the 60 students in the Boston public school systems in those 4 high schools who took the AP Physics exam, only 15% or 9 of them scored 3 or 4 or 5, which is what's considered successful, compared to about 40% statewide that scored those averages. This is not just a regional, but it's also a national problem. What we've developed is this blended MOOC, starting again with the edX AP Physics 1 project, into a partnership model where there's the university on one side and the high school on the other side. There's basically 2 components in the universities. There's a faculty, and there's also the undergraduate learning assistants. And on the high school end, there's obviously the student who are trying to meet their needs. Importantly, though, there's a high school liaison, doesn't do any teaching. I'll talk more about each of these aspects in a moment. But very important, the teacher liaison at the high school, and also the parents as a support network. We have 3 community building sessions. We had one in September. We're having one February 1st, another one in May, where we actually bring the parents, the uncles, the aunts, the students, the learning assistants, the professors, all on campus to have dinner together, do demonstrations, to talk about the program, about what we can do to succeed, and motivational aspects of the program. If I had more time, I'd love to show you how we've tweaked this to make it truly student engaging, so it's much more kinesthetic. It's intellectual risk-taking involved. We have every module begins with initial conceptions based on physics education research, based on the literature. We always have 2, 3, 4, 5 questions at the upfront, talking about things like if a big football player hits a small football player and they collide, who would experience the greater force? Almost universally, a student who hasn't studied physics, hasn't experienced some of these things, would say the smaller football player experiences the greater force, and it's actually equal forces, Newton's third law. And so we always ask these questions up front. We have pre and post testing is in terms of these initial concepts within each module. We use direct video measurements, which are terrific, in terms of on-screen, and if I had more time, I'd show you, but on-screen, basically, you see an object spinning around in a circle, a real object on a video spinning around in a circle. There's actually on-screen, there's meter sticks showing in the background. There's the frame counter, so they can measure time. There's the meter stick again, as I mentioned, and there's a force probe that's actually being used to measure the tension in the cable. And the students then can change variables. They can change the speed at which this thing is going about. And there's many of these kinds of experiments. These are as close as you can get to simulating a real experiment with these young people digitally. And we're not just going to make measurements. They have to actually analyze the situation. So in almost all of these experiments, the simulations as well, both built-in and external, the students are looking for functional relationships, not just verbatim making measurements. They're asking to change things, variables, and see how another variable is affected by that, and then to actually look for the algebraic functional relationship, the model, the mathematical model behind these experiments, and to build that knowledge on their own versus us just telling them. The actual module is also designed with the underserved population definitely in mind. There's things in the modules that would not be found in the typical. It's not found in our original AP Physics MOOC. For instance, we have built-in tutorials on how simply to convert units. Most of these students could not convert miles per hour to meters per second. They have no idea how to even attack that problem, which is something when you come on campus you already expect a student can do. You don't teach that, you just expect they can. These students would come on campus and have no idea how to attack that problem. So we model how to do this. We have built-in modules. They don't know how to use scientific notation. Again, another expectation if they come on campus, they can use scientific notation. They know how to work with it, manipulate it. Most of these students cannot. And so there's built-in modules that show them how to do that. Vector, signs, trigonometric functions. Again, these are things that are expectations. You can come on campus, you can do these. These students cannot in their present situation and would not if they didn't have this kind of experience to make them competitive. So we're trying to undo opportunities that are denied these students by offering this kind of platform to them. We also built in, every module has at least two homework, has a mid-homework, a final homework, a mid-quiz, a final quiz, and has at least on average, about 1.5 graded laboratories, as I've described, plus probably another 1.5 to 2 simulations where they're not graded, but they have to actually do similar things that we're talking about in these graded. We also do some scaffolding in the homework. For instance, again, I'd love to show you some of these things, but one of the first questions is a fairly complex questions that talks about how would you find, for instance, the tangential speed of the space shuttle, 250 miles off the surface of the Earth. There's hints. They can click on hints. So it says, think about Newton's second law for a special case for circular motion. Think about universal law of gravity, and see what you can do to put these two together to answer this question. And then the answers actually model that. The answers model the way we want them. So the two hints, the two laws are presented, the two laws are put together, the algebra is shown, and with answers and the units are placed in, and then the answer is demonstrated. That's a 1-point question out of, say, 20 points on a homework. The next question simply asks them, how do you find the speed now? In that first question, they found the speed. Now the second question asks them, how do you find the period of revolution? How long would it take the space station to get around? That's a simpler question. It's a much simpler relationship to be able to solve that problem. That's actually a 2-point question. It's counterintuitive. You think you give more points to the hard questions and less to the easier. We've actually turned that around. We give more points for the easier questions and less for the hard. So no student could really because they get grades in here too. They get actually a formal grade. No student can get a B or an A unless they can do the hard problems. But they have built-in success by having some of these easier, important questions still part of the homeworks and the quizzes and actually worth more points. Okay, so that's the MOOC itself. The near-peer tutors, these are learning assistants, undergraduate physics majors. So 17 of our 24 students in this pilot project actually come on campus once a week for 2.5 hours and get additional. By the way, I would tend to disagree that one-on-one tutoring is not, in my perspective, is maybe not the best model, maybe more 1-on-4, 1-on-5, 1-on-6, where you really can engage in small dialogue and discourse between the mentor-teacher, perhaps, and the student learners. And that's what this model gives these students an opportunity to do when they come on campus for 2.5 hours each week. They work with a learning assistant who has trained in a School of Education course on engagement and learning theory. They meet with the faculty. The learning assistant meets with the faculty for an hour a week to debrief and to get guidance on what should be done in this particular 2.5-hour week session. So there's a small group, built-in time for individual questions, and attendance is actually part of the grading rubric for these students. It's 20% of their grade, and as of now, for the first 16 weeks, we have about a 92% grading for these children, many of them coming from taking an hour to get to campus and an hour back, and we have a 92% attendance success for these young people. These are 8 of our 17 students. The group here is our Friday recitation group, and that's our Tuesday recitation group. So sometimes on the right, you see they're working actually with the MOOC. Sometimes they're not at all working with the MOOC, and there they happen to be just working with probably one of the most critical aspects of kinematics is dealing with force diagrams and successfully being able to draw those. High school teacher liaison is extremely important to us. They actually provide the vetting and the recruitment of the students. They work with the high school guidance office to make sure that grading, that the students who would not have this on their transcript, a condition of being part of the program is the school has to put this on their transcript. Every school we work with does not offer AP Physics. So it's not part of their program of studies. So their agreement is they will put this in their program of studies. The school will get this on their transcript, and they will get a grade, just like they get on every other one. They also have to have a time scheduled during the day. So if they have 45-minute blocks, then the teacher liaison makes sure they're the person responsible that these 3 students will get maybe Monday a block. They'll be in the library where they can get to the technology, and they will work on the program. The faculty here can monitor if they're doing that because we know when they're working on the program now, and we look at that and we give feedback to the liaison. They also are the person who would talk to the faculty and let us know when midterm reports are due, when end-of-term grades are due, and they do get midterm reports and end-of grades. So the liaison's a critical player, but they do no teaching allowed. That's one of the things we emphasize because we want to make sure the program does teaching. Okay. Measuring impact, we have 6 measures of impact. Our research focus is, can this kind of delivery system provide a success for kids taking AP Physics, and also can this be replicated? We think this is a potential solution that could reach 500 to 1,000 students per year in just the physics discipline. We think in the order of many thousand per year if also additional edX platform, other AP STEM programs could model off this. So we'd like to see this replicated. We're doing a proof of concept right now. We're looking for replication, and then we're looking for scalability on a national level and also to other AP STEM courses. And so there's a national problem, and we think edX and this platform and this model is a potential solution for many students who are denied these opportunities.